Good afternoon, everybody. Welcome to today's webinar. We're joined today by one of our partners in the US, Online Resources, and the topic of today's webinar, we're going to be looking at 3D scanning applications for the casting industry. A couple of housekeeping bits just before we get started. If you have any questions as we run through this webinar, feel free to drop them in the Q&A area in your Teams environment. You should see a little Q&A icon at the top. Ask any questions you want to in there, and we will field them at the end so you can get your questions answered. If we don't get round to giving you as detailed an answer as you would have liked on this call, just due to time constraints, we will make sure that we reach out to you afterwards to follow up. So without further ado, I'm going to pass over to JD and Cade from Online Resources to take it away.
Cool. Thank you very much, Guy. So I am JD Schomburg. I'm the president at Online Resources, and we've been in business for about 35 years, and we really have focused on 3D data collection and the hardware and software tools for that if people want to bring it in-house. So we're working with Geomagic today. We're going to be taking a look at Design X for some mesh editing, reverse engineering, as well as Control X for some inspection applications specifically to the casting industry. So today we have a part from Cunningham Patterns out of Columbus, Indiana, and they've given us an intake manifold that's an aluminum casting. We'll be looking at the mesh editing and some of the reverse engineering stuff there, as well as a Packard exhaust manifold, where we'll take that into a reverse engineering to design intent, and also some inspection quality control stuff there. So Cade Hill is the director of our engineering services, and he's going to be walking through the software tools for us.
Yeah. Thank you, JD. Like JD mentioned, for the mesh editing portion of the reverse engineering demonstration, we're going to be looking at this intake manifold that was provided by Cunningham Pattern. We won't do a full reverse engineering of this, just illustrating some of the mesh editing capabilities of the Design X software. This particular part provides us with some unique challenges. Namely, if we look down in the inside here, we can see that we have lots of missing scan data. You can see that there's lots of holes inside of here. And in fact, I've gone a step further and I've deleted the outer surfaces of the same scan. That way you can kind of see a little bit better what we're dealing with, how much missing data we have. One way we can overcome this challenge is using some silicone plugs. So on this particular part, we've taken some silicone plugs of the ports, and using the positive shape scan of the silicone plug, we can align that to the mesh of the actual intake manifold and fill in some of these missing areas. So I've already done a couple of them here. You can see that these ports, the silicone plugs, have been aligned. I'm going to demonstrate how this works using a third here. So I've got my third port. You can see it floating above the manifold here. If I go into the Alignment tab of Design X and choose Align Between Scan Data, I can start by using this Picked Points option, which allows me to sort of help Design X to understand where this port should be fitting on the mesh. So I'm going to go ahead and just pick a few points here and pick 3 similar points on this other mesh. Hopefully I'm getting in roughly the right area.
And this is one of the tools that Cunningham Pattern really speaks to, as the alignment capabilities of data and the powerhouse of Design X, and taking whatever data you need and aligning it different ways to get a single STL.
Right. This could be a few scans of the same part. This could be the example that we're doing here. You can do any sorts of alignments between many different meshes. So there, now I have the silicone plugs aligned and registered correctly relative to the internal surfaces of the ports, and as a result, also registered correctly with the external surfaces of the manifold as well. There's a few different other mesh editing tools that we can go into. For example, smoothing. If I wanted to remove some of the imperfections on the manifold, I can use my smart brush and simply smooth those out. You can see that these little marks here, very easy to smooth those out. There's several mesh editing tools, and I'd be happy to go over more of these with you, over email or phone call or something if you have more questions about these in the future. But once the mesh editing is complete and the mesh has been repaired and it's been enhanced, once it's been finalized and ready for the next stage of the reverse engineering process, we can move over to that stage. And I'll do that right now. So I'm going to open up another Design X file. What you're seeing here on the screen is the Packard manifold that we mentioned earlier. So the goal here is to take this exhaust and create a CAD model of it that can be used to manufacture new parts that are identical. In this case, it wouldn't be exactly identical because you can see this manifold is damaged. Over time, the manifold has heated and cooled and warped and eventually cracked, and you can see that it's been welded on the bottom side here.
And okay, this is a legacy part. So this is like a one-off that really can't be replaced.
Yes, right. Well, the goal is to replace
it. Yeah.
Right. But it is something that is difficult to get your hands on, and a lot of the data used for manufacturing doesn't exist. There's no drawings or anything like that. So we need to create a model that we can use to replace it. So what we're going to do is we're going to use the outside surfaces of this manifold, as well as the port locations of the engine, to recreate a model that is representative of the part on the outside, but isn't warped. We're going to use the ports here on the engine to make sure that it's going to fit on the vehicle. So I'm going to roll down this tree a little bit and show you what I've done. The first thing I did was I created a swept surface of the outside. So I'm just sweeping the main profile of the outside of the part. Then I've gone through and I've created the pucks, which are where the manifold will mate to the surface of the engine. At this point, I'm going to go through and do several other swept surfaces, which connect the main shape of the manifold to the pucks. And I'm going to roll through this a little bit quickly.
And this is, you're kind of like pre-baked here, pulling the cake out of the oven.
Exactly.
Things like that. But one of the things that I'm looking at is you have some areas where you need to be exact to the mating surface, and other areas where it's not going to be correct.
Correct.
How can you tell what's important, how accurate? Like if you need to be 5 thou accuracy to one area and you don't care about others.
Sure.
How do you do that?
Yeah, we can do that. So Design X is outfitted with a nice tool that's called the Accuracy Analyzer. And this Accuracy Analyzer allows us to see a deviation overlay of the model that we're creating relative to the scan data that we're creating it from. So if I make this a more reasonable number for the part that we're doing, you can see that everywhere in green is within plus or minus a value that I've specified. Everything that's yellow moving to red, the CAD model is proud or bonus material of the scan. Everything light blue to dark blue, the CAD model is shy or minus material. So you can see in these areas it's proud, and in these areas it's shy. And the reason for this is because due to the heating and cooling of the manifold, it's warped over time. So you can see it's actually slightly concave in shape, like a happy face or a contact lens or something like that. But
happy face,
right, we've made our model perfectly straight to mate and match with the engine perfectly, and we've chosen to ignore any deviation in these areas because we know it's not correct.
Cool.
So going to move forward here. What I've just done here is I've done a surface offset. So the customer actually asked us to make this part a uniform 1/4 inch wall thickness. So that surface offset is just an offset at 1/4 inch to make sure that all of the internal passageways give us a uniform wall thickness.
And that's another thing I think is important. We talked a little bit about the internal surfaces using the plug on the aluminum casting here.
Yes.
but in this case, you wouldn't be able to pull a plug.
Right.
So
Yep.
what are some of the, I guess, processes that people have used to try and get those exact surfaces in it that have been successful?
A lot of times when we're doing the reverse engineerings of the castings, people just ask us for a uniform wall thickness. If that's not the case, and there are some unique geometries on the inside surfaces of the part, the unfortunate reality in some cases is that the parts need to be sacrificed in order to collect those.
Okay.
Many scanning systems are all line of sight, so if there's any deep passageways that you can't collect, in some cases, if we can sacrifice the part, that's one of the options. Another option would be to use a CT scanner of some point. That's been used as well to get the internal passageways.
So a few different options
Yes.
that varying range and price, and
Mm-hmm.
in this case, I believe the part was already destroyed.
Right. Right.
So sacrificing this part was an acceptable
Right.
option.
Right. So here I've just finished up the machined version of the model. So the model that I've created here is from a finished machined part. So the resulting CAD model will be a finished machined part. The people that we did this for, they wanted us to also create for them an as cast version of the same model. So these next few operations I'm going to show you are going to be adding machine stock in the necessary locations to create the as cast version of the model as well. So I'm just going through and adding some extrusions onto some of the pads. You'll see that over here on the outlet, I've added some machine stock to those surfaces as well. Anywhere where they're going to do a machining operation, I've added the necessary machine stock to this part and added the necessary fillets and rounds to knock off any sharp edges.
So we're really looking at a full model here that the customer asks for specific stock, specific things like that.
Yep.
There are some other applications, I mean, draft angles,
Yep.
Things like that, that it is really customer dependent.
Mhm.
So a lot of times we'll just send, this kind of, I'll call it a raw file,
Yes.
or a finished machined
Mhm.
file.
Mhm.
And then the customers will add their knowledge to that file to make
Right.
sure that it's correct for
Yeah.
the casting process.
Yeah, I mean, we aren't like casting professionals necessarily. We
Correct.
don't live in the industry, so during the reverse engineering process, especially on a part that's been damaged or a part that's very, very old, a legacy part, there may be some assumptions made that are incorrect during the reverse engineering process, and that's just a conversation that needs to happen with the customer. Either I can make those changes with some direction, or we can send the sort of raw model to them, and they can make those changes themselves. One of those options is perfectly viable. So
Cool.
So here we go. We have two finished models. We have the as cast model and the machined model. In this next example with Control X, we're going to be giving an example of what happens after the part has been manufactured using this CAD model. So we're going to pretend here that we have cast a new manifold, and we're going to compare that manifold back to the nominal CAD data that was used to create it. So I'm going to pop open Control X here.
Cool. And while you're doing that,
Mhm.
I think there's a lot of cool things that can be done with the Control X. So I want to give kind of a lead in here.
Mhm.
One of the things that I've seen is most successful here is being able to align to different datums.
Right.
So is it your casting datum? Is it
Right.
your machining datum? If your customer has a different alignment they would like, and it allows you to export that all in one report. It's very quick, it's easy, but it really gets everybody in the room on the same page with one report looking at
Right.
all the different options. And that is where I think the communication ability and tools of Control X are really market leading in that kind of aspect. So
I agree.
that's a little lead into that. So we'll go ahead and let you show off the Control X stuff
Yep.
now.
And I've worked a little bit ahead here, but I'll explain what I've done. So basically, what I started with there was an initial alignment. If you saw when I very first opened the software, the CAD model was down here in the world space coordinates where it was modeled. The scan data was floating somewhere up here in space, and that's a very common thing with 3D scanners, is that the scan is not going to be automatically aligned to the CAD model when it's brought into the software. So the first thing that I did was an initial alignment just to get the scan data close to the CAD. And now what I'm doing is I'm going to be following it up with a secondary alignment that I'll use for my analysis. So we're not going to stop with the initial alignment. We're going to apply an alignment to the scan relative to the CAD that makes sense to us, something that maybe in this case simulates the manifold on the engine. So what I've done here is made a plane on the mating surfaces of the flange here. And then I've also grabbed two circles, one circle on this first port and one circle on this last port here. And what I can do using those features is I can do a datum alignment. So I'm going to go into my datum alignment and I'll choose some datum pairs. My first pair, I'll make this plane. And then let me hide the CAD model so I can see this a little bit better. I'll choose my circle 1. I'll make that a point. And then circle 2, I'll also make that a point. And then I'll click the checkbox on this. And that will adjust the scan in space so that it's aligned to the CAD model, using those datums. All right. At this point, I am free to do any sort of analysis that I want. So we're just I'll just do some, I guess, random-ish measurements here. Let's go into the dimensions tab and I'll choose a radial dimension. And I'll go ahead and just click this cylinder here and it's going to pull the dimension from that. Right now it's tolerance at plus or minus 0. Maybe we make this plus or minus 10 thousandths or something like that. Come over here. Maybe we want to understand how tall one of these pads is to the mating surface here. What I can do is I can create a simulated CMM point, which simulates a CMM coming down and touching on this pad here. Let me hide the scan so I can see the pad a little bit better. Something like that.
And I just noticed, so you're actually extracting or setting up your inspection report on the CAD model here.
Correct.
So this is something that you'll do once with the CAD model, and then you'll be able to just drop in scan data. So if this is a part you need to inspect over and over again, and it's not just a one-off, you'll be able to do that basically in the time it is to import the scan.
Right. Yep. So this
automatically runs.
That's correct. So this program kind of lives forever, so to speak. So once we save this program, all of the dimensions are attached to the constant, which is the CAD model. So what that means is that when you're ready to do more inspections of other parts, the only effort that you have in running this program and measuring those parts is whatever time and effort it takes to scan the parts. At that point, once the scan is complete, you can simply replace this scan data. Come in here and say replace measured data, and you can replace that scan data with new scan data, and the program will run automatically. So it will perform the initial alignment, it will perform the datum alignment, and then it will extract whatever dimensions you're interested in seeing.
So that's similar how like the CMM setups work,
right?
Where once you program the CMM, you then just have to have a little more time fixturing and doing that, but it'll just rerun the same part.
That's right. So one of the last things that we like to do, or actually one of the first things in many cases inside of Control X, is adding a color map. So color mapping is something that's very descriptive. It can tell us the gross deviations between the scans and the parts. So again, let me set up a tolerance that makes sense here. Oops. Sorry about that. Let's make that 0.1. There we go. Maybe we make this a little higher so we can get a more gradation of colors. Let's make that something like this. There we go. So now we got a nice rainbow pattern of some colors here. And at this point in the color map, we can click on the CAD model to annotate. So if I come through here and I say, what's the specific deviation in this, that, or the other area, I can come in here and click on the model. Turn on that color map here. Go. We can organize these a little bit. So we're going to pretend now that the analysis that I want to do is complete. I'm going to adjust some of these annotation flags so we can see them a little bit better.
So as you're adjusting that, I do have a couple of questions because there are some things happening on the screen that there are a lot of different colors and things happening.
Right.
So in these points that you've just selected, those colors are relative to the deviation bar on the right side of the screen?
That's correct. Yep.
Okay, and to what you set that.
Yep. It's
to
a
read.
it's a user defined tolerance. Like let's say we have a surface profile tolerance of 60 thousandths. I would adjust that to plus or minus 30 thousandths.
Okay.
And that would be your overall surface profile of the
And
part.
so this is really where, like, if you just need to know roughly, do you have enough stock?
Right.
A color map could say that for you.
Yes, correct.
Okay.
Yep. Yep.
And then the other thing that we've done is dimensions.
Mhm.
So some of those dimensions, I see a red, I see a green, and I have seen like a yellow or orange
Yep.
before.
And I'll adjust this one so you can see that as
Okay,
well.
cool. So the red, obviously, I'm guessing is out of tolerance.
Correct.
Green is in tolerance.
Yep. And then I have this yellow color here. I've adjusted the tolerance so that it turns yellow. What this means is it's a warning tolerance, and that is a tolerance that's greater than or equal to 50% toward a failing tolerance.
Okay.
So let's say your tolerance was 20 thousandths and you were at 15 thousandths out, plus or minus. It would be a warning tolerance.
Nice.
Just saying, this is close, but you're passing, but it's getting closer. So I've set up a single view the way that I want to see it on the screen here. Let me adjust this down a little bit. Also, another quick note about the color maps inside of Control X. The Control X product is actually the inverse of the Design X product. So the accuracy analyzer inside of Design X, it's looking at CAD versus scan. Here we're looking at scan versus CAD. So inside of Design X, these blue patches were red, but they're blue here because we're analyzing in the reverse direction. It's the inverse. So I'm going to go ahead and generate a report really quick. But first, let me create a snapshot of this viewpoint. Okay, and I'll go ahead and generate a report. And here I'm going to tell the software what I want in my report. We can do all of these different things. Let me actually generate this and just show you what it does by default.
So as that's coming up here, there are going to be a couple things. I'm seeing a couple questions come in already.
Okay.
That we'll go over just in a quick review.
Sure.
So.
Do you want to ask those now? Or?
No, go ahead.
Okay, sure.
Since that
okay.
popped up.
Great. Yeah.
We are live, so I'm trying to kill time.
Right. No worries. So by default, the Control X gives us a data that shows a page that shows the reference data, a page that shows the scan data, lots of statistics about all of our alignments. We've got some groups that show some statistics about the circles that we created in the simulated CMM points, all sorts of things. A lot of this I find just kind of muddies the water a bit. It's a lot of extra information that when you're trying to have a very quick and simple conversation with your customers or your coworkers, things can kind of get messy. So one useful thing that we can do here is when we go to generate a report, we can add and subtract things that we want to see and don't want to see. So let's say I wanted to just see my dimensions and my color map. I can just remove everything except for my dimensions here. And when I click generate, it will bring up this group 1 with my dimensions. But what I can do now is I can click on this and delete it. And I can insert the image that I took earlier. So now I have all of my color map annotations visible, showing the deviations in specific locations, and a nice clean view of the 2 dimensions that I care about, along with the table below them showing some additional information. And
I think that editing capability, when I talked about the simplicity of the Geomagic branded software, is really Control X. It's insane how easy it is. It just makes sense.
Yep.
And so like dragging those image over, deleting them, editing different tables is almost like editing a Word document.
Yep, it's exactly like editing a Word document. And it's the software, both Design X and Control X, were designed to be as user-friendly as possible. And that's the reason why we like it.
Yeah.
So.
Cool. So now that you have this report, it could be PDF.
Yep.
It could be Excel, CSV, really whatever kind of data dump you need.
Yep.
Right.
Yep. So I can export it as Excel, a PowerPoint, a PDF. You also have the ability to export it as another file. I think it's an XML document. and those can be brought into a kind of sort of a trend analysis inside of Control X to do trend analysis and see how dimensions are changing over time and stuff like that. It's sort of kind of like a process control sort of situation.
Cool. So that is a real quick overview of both softwares. There is something I want to go back to in Design X.
Okay.
And I think this was actually came in as a question and then realized we didn't go over it. So
what one do you want to see?
let's go ahead and back to the Packard.
Okay.
And let me get that pulled up here real quick. So when you need to make a change to this downstream, do you have to go back through this whole editing process in Design X? Let's say you're going to SolidWorks. How do you make those small changes and what needs to be done there?
So to make small changes, it can be done in Design X if you want to. All of this feature tree here is what's called rollable, or I'll call it rollable. I guess you can roll back and you can roll forward. And what that means is let's say I wanted to change some characteristics on this fillet here. If I roll back to this fillet, actually I've just rolled back a little bit too far. What I can do is I can double click on this fillet and I can change something about it. So this is a big variable fillet here. It changes as it goes around the part. But let's say I wanted to take this section of the variable fillet, and instead of make that a half inch radius, let's make this a 0.35 inch radius. And it will adjust that down to match what I've chosen. And then that change will roll forward to the remainder of the model once I roll it forward. So once I click roll forward here, excuse me, roll to the end. I'm sorry about that. Once I roll to the end, that change will be present in the finished model as well.
Cool. And then there's another thing
Yes.
called live transfer.
Right. Yep.
This
I think
is
that's what you were trying to get at.
Yeah.
I think that's what you're trying to get at.
Feed it to you.
Yeah, no worries. Okay, so live transfer is very cool. So what live transfer does basically is inside of Design X, we are building this model using all of Design X's modeling operations. And all of these operations that we're using here, fillets, sweeps, revolves, extrusions, all of these modeling operations exist in other CAD packages as well. And what that means is that Design X can do what's called live transferring into other CAD packages. So you see I have this live transfer button here. And when I drop that down, there are several available. We've got SolidWorks, Creo, Inventor, NX, and AutoCAD. Unfortunately, I don't have any of those software packages here on my work computer. I only use Design X. But if a user of Design X has one of these softwares on their computer as well, what they can do is they can click the live transfer button and they can either say start from first feature or resume from selected feature, or they can select some number of specific entities in the tree. And when they click the checkbox button on this, what it will do is it will open up SolidWorks in the background and it will rebuild the model inside of SolidWorks using all the same operations you used, but without any user input. It'll be as if you built this from scratch inside of SolidWorks, but you didn't. Yeah.
Cool. Yeah. And that is a very powerful tool, especially when we're doing some service work for somebody and they don't have Design X to go back to. We call that a smart model.
Yeah, something that's editable. Yeah.
And then when we just export like I just step Parasolid, we usually call that a dumb model because they can still interact with it, do their basic cutting.
Right, like they can cut it in half. They can add to it, like add bosses. They could use surfaces to trim things off of it. But the smart model, you have that added layer of editability that allows you to go in and like push and pull specific things, change diameters of things intelligently and stuff like that inside of your native CAD package, which is cool. So, and it is also nice to just when you're a SolidWorks house, having all of your models in SolidWorks is something that's very convenient. So,
cool. And then we didn't go over a lot of. We're going through this pretty quick, so sure. I think we'll probably be done a little early here. But are there any other tools that you'd like to show in the mesh editing capability?
Yeah, I can do that.
I knew we really zoomed through those, and that's a really powerful area.
Sure.
And maybe some alignment things as well.
Okay, great. So We have some other mesh editing tools that are available to us. I've already showed you the Smart Brush. I can show you that a little bit more here. So with the Smart Brush, the primary use case for the Smart Brush is this smoothing option here. And let's say I have some areas of the part that I wanted to smooth out. You can see that there's some, imperfections here that we can smooth. There's also a defeature option as well. So I'll perform a selection. Let's pretend that we wanted to remove this sort of bolt that's in the part right here. If I come in here and make a selection first, something like this, I tell the software that I want to defeature this. What the software does is it removes what I've selected and it replaces it with a patch of tangent geometry. You can set it to flat, you can set it to curvature. I can do the same thing over here on these bolts. Let's go ahead and make a selection like this and say defeature. Actually, I may have selected some of the inside of the part here. Let's be a little bit more careful with that. I end up actually doing the same thing again and removing from my selection too. Let's just go over here and sorry about that. So let's defeature this.
So this is, I mean, to me, this is one of the coolest things, to be able to get that clean, flat surface, and then you can, when you go into your CAD modeling process, you then have a clean surface to work from.
Right. You don't have any of these objects in your way. You also mentioned alignment. So what I've already done here is I've taken this scan and I've aligned things to it. But remember what I said earlier in Control X about the scan data not being in the correct location.
Yeah.
So this part conveniently is already aligned, but let's pretend that it wasn't. Let's get rid of all of these things. I'm going to clean up my workspace just a little bit here.
And I appreciate you.
Yeah, sure.
Kind of going.
Yeah, no worries.
Off script here to.
Yeah, no problem.
This.
Let's move it somewhere like this. Okay. So we've moved the scan. This is what you're going to see when you bring a scan into Design X, especially if you're using a handheld scanner. Some scanners that, are tripod mounted or whatever, you can set up, or like a ferro arm of some sort, you can probably set up your coordinate system beforehand. But with handheld scanners, you'll have data that's floating out here in space. So our job now is to align it to the origin in a way that makes sense. So
when you go to like front face,
right,
you can do your
that, and also when you finish the model then will be on the origin.
Oh, okay.
So that the model is in the correct model space.
Cool. So when you bring it into SolidWorks or something, you don't have to redo this.
Right. Or when you have your machined model and the person who's writing the program for the CNC machine.
Okay.
That will they have like a true 0 point they can go from that makes sense relative to the machined features. Cool. So let's go ahead and create a plane. So here you'll notice I'm actually not extracting things from the CAD model because we have no CAD model to extract from. Instead, what I'm doing is I'm selecting scan faces. Oops, sorry about that. And I am doing what's called region grouping. So region grouping is something that's very unique to Design X. And what region grouping does is when I insert a region on a selected area of the scan, it identifies that as a selectable patch. So now you can see I can select this region here. And when I hover my mouse over it, not only is it selectable, but Design X also estimates what kind of feature that selected area is. So you can see next to my mouse it says plane. So if I select that now, I can go to my model tab and create a plane. So let's click on plane. And I'm just going to extract a plane from this region. So let's preview that. You can see it shows you highlighted a light blue color, what points on the scan it's best fitting that to. Okay, so there we have a plane. Now, when I create a sketch on this, that sketch is going to live on this plane. This is the plane where that sketch is going to be, irrespective of how far up or down I take this cross section.
And that's, let me ask this. It's going to be on that plane because you've selected it.
Yes, right.
So you get to choose what plane it projects to.
Yes, and that'll make more sense when I go into my next step. So what happens now is I'm going to do a sketch on this plane that I can create 2 perpendicular lines on, and I'll create a coordinate system from those 2 perpendicular lines. So let's do a sketch, and I'm going to do a mesh sketch. And this is another thing similar to the region grouping that is very unique to Design X. If I go to mesh sketch here, you can see that Design X is showing me a cross section of the scan, and I can grab this arrow here and drag this up or down. Now I'm choosing where on the mesh I want to take this cross section. I'm going to go up into these bolts. I'm just going to use these bolts for my alignment features here. And when I hit the checkbox, no matter where I've dragged that cross section, it projects it back down to where that plane started, which is exactly what I want, because I want this plane here to be my Z0. When I create 2 perpendicular lines, one line between these bolts and one line starting from this bolt perpendicular to that, that will be my positive X and my positive Y direction. So let's first start by creating some circles on these bolts that I can put some lines between. So I'm going to hide my mesh for just a second so I can see these previews a little bit better, these preview pink raster sort of preview circles. What I'm going to do now is go into my circle creation tool and simply double click on these. Like that, like that. So what Design X has done here is any of those circles that I've double clicked, it best fits a vector circle to that, an actual CAD sketched entity.
Cool.
Yes. And now I can make lines between those. So I'll make a line between this center point and this center point, and I'll make a line starting from this center point perpendicular to that line. And you can see that perpendicular constraint has been applied there. So now what I have is I have a sketch going between these bolts and then out this direction here. And that sketch is what I will make a coordinate system on. So let's go ahead and hide my scan again so I can see this just a little bit better. And under my model tab now, I'm going to create a coordinate system. My origin will be that circle center point. I'll choose positive X here, and I'll choose positive Y here. And you can see there's my coordinate system. Now my Z is facing the wrong direction, unfortunately, so I'm actually going to flip X here, and that will flip my Z. So now Z is pointing up away from this face instead. And here I can do an alignment. So again, I'm going to show you where these reference planes are. You can see my front, my top, and my right planes here are all intersecting each other way over here. So my scan is not in the correct position yet. But when I go to my alignment button and choose data match, it's going to ask me what I want to move, and I'll say I want to move the intake manifold, and I'll go to my next stage of this operation. And I'll zoom this out so you can see it happen on the screen. When I select my coordinate system 1 that I just created on the top of the part and hold the control key and click the origin, you'll watch as the scan snaps into position at the origin, just like that. So on this right-hand side, it just kind of snapped over to the origin. So now my scan is in the correct location, and I can begin my reverse engineering process.
Very cool. So just a few extra minutes on the front end makes it a lot easier on the back end.
Yep. There's nothing stopping you from modeling it right in space where the scan is, but then you've got this model that's kind of floating out here in space, and you need to reorient it anyway to do anything with it. So I would prefer to just do it up front to the scan data, model everything in the correct position right away.
Awesome. So I think I'm looking at kind of the time and keeping track of that, but one of the questions I had, we've talked about SolidWorks, and for Design X, probably people who are interested in utilizing Design X in-house have some kind of CAD experience, have a CAD program. It is very powerful, but it's also pretty easy to use. So how long does it take someone to really ramp up and become, we'll say, dangerous?
Yeah. Somebody with CAD experience, we could probably have them up and running in 2 or 3 days, depending on their level of expertise. Somebody who is starting from absolute zero, that's a little bit hard to say, just because the beginning of the training would be mostly like getting lingo
Yeah.
and like jargon
Yeah.
together and explaining how like the theory kind of behind what we're doing before we actually get into the button clicking. But if somebody has CAD experience, yeah, I mean, it's very, very quick, just a couple days.
Cool. So that is pretty much the overview we had for Design X and Control X. So Design X being the reverse engineering tool, Control X being the inspection and quality control tool. We are going to be at Cast Expo. I believe that's in Atlanta, and we'll be at booth 2826. So if you guys are going to be there, we're going to have this part there live from Cunningham Patterns. We'll have some of the plugs to go over that from a data collection standpoint. We'll also be going live with people through. So if you have very specific needs, specific questions to your process, like some of the things we didn't talk about today was everything we've done here could be done on patterns,
Right.
corners,
Oh yeah.
and analyzing the core to the final part.
Yeah.
So
Yep. We've done plenty of stuff like that, like in the past, you know, create like for people who do the sand printing, you know, taking the core box and scanning both halves of the core box, putting those together, deleting all of the external surfaces so that you're left with the inside surface, and then modeling that so that you have the actual core from the core box. So you can, instead of scanning the core, you can scan the core box halves and get the core as a model to have printed.
Very cool. Yeah, so a lot of stuff. And I think that's, again, I don't want to jump too much into those details, but feel free, if you're not going to be at Cast Expo, feel free to connect to us if you do have, connect with us if you do have questions and specifics there. We'll be happy to walk through those with you and maybe hop on a Teams meeting.
Okay.
So yeah, Cade, thank you very much.
Yeah, thanks for having me.
Doing that.
Of course.
And again, we're online resources. I'm JD Schomburg. This is Cade Hill, and I'm waiting on giving Guy kind of the signal to prep. I know there are a lot of questions coming in, which is exciting. I like to see that. So we'll go ahead and pass it off to Guy on.
Thanks, everyone.
Thanks, guys. That was great. Yeah, as they said, if you've got any questions, feel free to drop them in the chat now. I think the extra workflows that you showed have answered some of the questions in there already. Just checking the Q&A box, seeing if there's any other. Doesn't look like any more have come in. If you have questions, if you think of questions after you review this afterwards, we'll be sending out the recording to everyone that's joined the webinar, so you can review and share with anyone else that you think might be interested in this. And if you've got any other questions, we'll make sure to add contact information so that the online resources guys can reach back out to you. But if there is no other questions, I think we can finish the session now. Thanks, JD. Thanks, Cade. Really, really useful, really interesting. Thanks everyone for joining, and hopefully see some of you at the Cast Expo.
It's good. Thanks, Guy.
Thanks, everyone.
Cheers, everyone.